Welcome to the Deep Dive, where we cut through the complexity of groundbreaking research and extract the knowledge that truly matters. Today, we're plunging into a silent crisis brewing beneath our hyper-connected lives, the hidden traffic jams on our invisible airwaves. You might not see them, but your phone, your smart home, every wireless device you own relies on a finite resource, the radio frequency spectrum. And here's the paradox. Global demand for wireless services is absolutely exploding, yet vast swaths of this precious resource sit idle,
underutilized, like empty lanes on a jammed highway. This isn't just inefficient, it's a bottleneck, holding back the next generation of wireless innovation and a significant waste of a foundational global.
And this is precisely where the revolutionary concept of cognitive radio, or CR, steps in. Imagine a radio that isn't just a passive receiver or transmitter, but an intelligent, adaptive system capable of understanding its environment. Its fundamental idea is to solve this problem of underutilized spectrum by allowing secondary users to think your personal devices, or perhaps a new, agile wireless service to intelligently access these licensed bands when the primary users, those who hold the official license, are inactive. The crucial part.
It does all of this without causing any disruptive interference to those primary users. It's about implementing smart dynamic spectrum sharing.
Okay, let's unpack this, because the core challenge here is immensely complex, isn't it? If a primary user signal is really faint, almost indistinguishable from noise, how do you reliably differentiate that from just an empty channel? What's the biggest challenge in truly knowing if that lane is clear or if someone's just driving very, very slowly, almost imperceptibly? That's the big question, and that's exactly what we're diving into today. Our deep dive explores how we can make these cognitive radios even smarter, more efficient, especially when they're operating in really complex, unpredictable
wireless environments. Our focus is a fascinating research paper titled Performance Improvement in Wideband Spectrum Sensing Under Fading, Use of Diversity by Kamal Kaptan and Manjunath Joshi.
Our mission today is to understand the innovative ways this paper proposes to significantly improve a critical function called wideband spectrum sensing, or WSS. They achieve this by leveraging a powerful and often underutilized technique known as diversity. This diversity is key to effectively combating fading, those tricky and often frustrating fluctuations in signal strength that plague wireless communication, making reliable detection incredibly challenging. We're talking about pushing the boundaries of wireless communication, making it not just faster,
but fundamentally more reliable and more efficient in the face of these real-world environmental obstacles.
So let's establish the high stakes here. The paper opens by stating a very clear truth that resonates deeply with our digital lives. The demand for radio frequency spectrum is increasing at an explosive, almost insatiable rate. This isn't just about faster downloads, it's the foundational invisible infrastructure that powers our entire modern society. Every time you stream 4K video, connect your smart thermostat, rely on GPS, or communicate using your mobile phone, you're tapping into this limited resource. Without an efficient way to manage it, we face a future
where bandwidth becomes a critical bottleneck, hindering innovation, limiting economic growth, and potentially even compromising public safety services that rely on reliable wireless communication.
And that's precisely where the paradox truly hits home. While we're seeing this unprecedented demand, the reality is that the vast majority of usable RF spectrum has already been allocated and licensed. Governments and regulatory bodies decades ago assigned these frequencies to specific entities, think major broadcasters, established mobile carriers, emergency services, and the like. But here's the kicker, as the paper points out, citing reference one from extensive empirical studies. It's been consistently found that many of these licensed bands are actually underutilized.
They sit dormant for significant periods, sometimes hours, even days, leading to a massive wastage of a truly finite and incredibly valuable resource. It's the classic supply and demand problem.
That's why the highway analogy is so apt, though perhaps even that doesn't fully capture the complexity. Imagine a bustling metropolitan highway system where entire lanes are permanently assigned to specific companies. Company A gets lane 1, Company B gets lane 2, and so on 24/7. But Company A only needs its lane for a few peak hours in the morning and evening. For the rest of the day, that lane sits completely empty, perfectly paved, perfectly functional, even while the other lanes are jammed with traffic. The RF spectrum operates in a very similar,
almost bafflingly inefficient way. These license bands are reserved, their own, but often the actual primary users aren't transmitting on them. They're empty, yet off limits to anyone else.
And that's precisely where cognitive radio, or CR, emerges as incredibly clever, adaptive, and dynamic solution. Instead of fixed static allocations that lead to this tragic underutilization, CR provides a way to make spectrum usage intelligent and responsive. At its core, it allows secondary users, again, your smart devices, an IoT sensor, or perhaps a new broadband provider looking for a clear channel to temporarily access these licensed bands. But here's the critical, non-negotiable part. They can only do so when the primary users
who hold the license are definitively inactive. It's like our highway analogy. But now, a smart real-time traffic management system can dynamically open up those unused lanes for others, as long as it ensures...
Absolutely, and for the cognitive radio to be truly functional, to effectively act as that smart traffic manager, its main task is something called spectrum sensing, or SS. This is literally the CR's ability to listen and detect the presence or absence of the primary users with extreme precision. It's like having highly sensitive, almost omniscient ears that can tell if a channel is genuinely free, or if there's even the faintest whisper of a primary user's signal that might indicate an impending transmission. Without reliably performing this
listening act, a cognitive radio cannot operate without potentially causing disruptive, unacceptable interference, which would completely undermine its entire purpose and regulatory viability.
And thankfully, primary users often use their licensed bands quite sparsely, creating what the paper refers to as spectrum holes. These are those temporary unused slots that secondary users can opportunistically jump into. Over the past decades, many techniques for spectrum sensing have been investigated, each with its own trade-offs. However, the paper, like many practical CR implementations, focuses on a common and remarkably simple one called energy detection, or ED. The reason for its widespread popularity and its adoption here
is twofold and deeply pragmatic. First, it's a non-coherent technique. For those familiar with signal processing, you know a coherent approach, while potentially offering higher...
far more pragmatic and robust for the rapid adaptive decisions a cognitive radio needs to make in a constantly changing environment. Second, its simplicity makes it incredibly easy and cost-effective to implement in actual hardware, accelerating real-world deployment.
So, if we equip our cognitive radio with these super-sensitive ears, what's the next frontier? Can it scan not just one potential spectrum hole, but an entire landscape of possibilities simultaneously? What kind of challenges does that wideband ambition introduce? That's where wideband spectrum sensing, or WSS, comes in. Instead of sensing a single narrow frequency band, secondary users employing WSS try to monitor multiple frequency bands at a time. The ultimate goal, to find multiple spectrum opportunities, or
SO, all at once. This broad, panoramic view is essential for a secondary user that might need to transmit over a larger, aggregated bandwidth, or simply wants multiple backup options for robust communication.
However, this broad view, while desirable, comes with a significant practical hurdle for traditional sampling methods. To accurately sample a wideband signal, you typically need to adhere to the nyquist sampling rate, which dictates that you must sample at twice the highest frequency component of the signal. For a wideband, this rate can be incredibly, prohibitively high. We're talking about needing extremely fast analog to digital converters and immense processing power, which can be practically challenging and astronomically expensive to implement in
real hardware, especially for power-constrained mobile devices. Past research has attempted to overcome this, for example, by using compressed sensing, or CS, which aims to acquire...
So here's where the paper takes a pragmatic and incredibly clever turn. It acknowledges a crucial real-world insight. In many scenarios, a secondary user may not actually be interested in finding all the spectrum opportunities across the entire wideband. Instead, their interest might lie in finding just a sufficient number of opportunities to meet their current communication needs. For example, your device might just need one clear channel for its current transmission, not dozens of options. This leads to the paper's adoption of partial band Nyquist sampling, or
PBNS. The beauty of PBNS is that it samples only part of the wideband instead of the entire wideband, thus significantly reducing the required sampling rate and the associated hardware demand.
Brings us to one of the most persistent, frustrating, and unpredictable challenges in wireless communication: fading. Here's where it gets really interesting and messy, because in practice, the received signal almost always undergoes fading. Imagine you're on a phone call and suddenly the person's voice gets muffled, then loud, then it disappears for a moment, only to return with a different tone. That's a real-world experience of fading. Scientifically, it's a phenomenon where the strength of a wireless signal fluctuates unpredictably
due to environmental factors like multipath propagation. Signals arriving via multiple paths, interfering constructively or destructively. Shadowing, blockages by buildings or terrain.
Directly to the critical research gap this paper fills. While some limited prior work has been done on wideband spectrum sensing, considering fading, as referenced in the paper, and previous work analyzed existing algorithms in fading channels, none of these approaches considered a crucial, powerful technique that could profoundly impact performance: diversity reception. This is the paper's critical insight, almost a call to action. It notes that, quote, "It may be of interest to note that the performance can be improved by using diversity reception."
Quote, "This sets the stage for their crucial contribution, systematically bringing the power of diversity to the complex challenge of wideband spectrum sensing in the face of..."
One path for the signal is blocked or weakened or fading out due to environmental factors, another path might still get through strong and clear. Think of it like this. If you wanted to make absolutely sure a critical message reached someone, you wouldn't just send it through one channel on one route. You'd send copies via several different routes, perhaps through different mediums, maybe an email, a text message, and a physical letter. Even if one path fails due to an obstacle or a weak link, others are likely to succeed, significantly increasing the probability that
the message arrives intact. That's diversity in action applied to radio signals. This redundancy, this multifaceted approach, is incredibly powerful in overcoming the unpredictable nature of fading.
Exactly. And in the world of wireless, there are very sophisticated diversity schemes, each with its own trade-offs in terms of complexity and performance. Some are very complex and computationally intensive, requiring detailed knowledge of the communication channel, like maximum ratio combining, or MRC. MRC is considered optimal in many scenarios because it weights and combines the signals from multiple paths precisely, but it demands complete and accurate channel state information, which is often difficult, if not impossible, to acquire in a dynamic
CR environment. Other schemes are simpler. The authors of this paper specifically chose square law combining, or SLC. This is a non-coherent diversity combining.
Combines the measured energies from multiple diversity branches, creating a more robust and statistically more reliable decision statistic compared to simpler selection methods like square law selection diversity. You just pick the strongest branch. This makes it a balanced choice for opportunistic spectrum sensing.
And this brings us to the core innovation of this paper: adapting this powerful concept of diversity, which has seen success in other areas of wireless communication, to the specific and incredibly challenging problem of wideband spectrum sensing under those tricky, unpredictable, fading conditions we just discussed. It's about making the cognitive radio's ears not just more numerous, but fundamentally smarter at combining what they hear to make better, more confident, and more reliable decisions about spectrum availability.
This isn't a minor tweak, it's a significant architectural enhancement for robust CR.
Building on this, the paper proposes two novel algorithms that explicitly utilize SLC diversity.
Let's start with the first one, CC-SLC, which is algorithm 1 in the paper. We can walk through it in pretty simple terms to visualize the process. Imagine you have P diversity branches, so perhaps P different receivers or antennas, and each of these is simultaneously listening across L different subbands within your designated partial band. The first step is to compute the energy for each of those L channels from all P diversity branches. So, in essence, each of your P receivers independently measures the energy present in
Each of the L subbands. It's like getting P different independent readings for each of the L channels you're monitoring. These readings individually might be affected by fading on specific paths.
TM value for each channel is now a much more robust and reliable indicator of whether there's a signal there, because it's the combined statistically average sum of what all your ears heard for that specific channel, mitigating the effects of individual fading paths. Finally, in step 3, you make independent decisions on all L channels using the energy detection method based on a predefined threshold. If the total combined energy for a channel, that TM value, is below that threshold, it's declared free or OF for secondary use. Otherwise, it's declared occupied
or ON. It's a straightforward application of energy detection, but powerfully enhanced by the diversity combining.
So with CCSLC, the final decision for each channel is made independently, which simplifies the overall logic. However, the crucial benefit comes from the fact that for each specific channel, you're combining the information provided by multiple diversity branches before making that decision. This combined information, robustly represented by T, makes the energy measurement for that channel far more resilient to fading and background noise, leading to more accurate individual channel decisions compared to a system using only a single antenna or diversity branch.
Now let's move to algorithm 2, the ranked square law combining, or RSLC. This one introduces a really clever and strategically intelligent twist. Steps
But then comes the smart and differentiating part, the ranking. In step 3, instead of immediately making decisions, you sort all the selected channels in ascending order with regard to their TM values. This means the channels with the lowest measured energy are put at the very top of your list. Why is this so brilliant? Because they are the most likely to be genuinely free of primary user activity. They represent the clearest, quietest opportunities available. Then in step 4, and this is the fundamental difference, you don't make decisions on all
L channels. Instead, RSLC only makes decisions for the first LD channels on your sorted list, where LD is a number between your desired number of spectrum opportunities, SD,
What's truly fascinating here is that this ranking and selective decision-making allows the secondary user to prioritize finding the clearest channels rather than attempting to clear all of them, which is a major efficiency gain. This isn't just about finding free channels, it's a fundamental shift in how cognitive radios can operate. Imagine a future where your smart devices aren't just reacting to a crowded airwave, but proactively and intelligently scouting the clearest path, conserving battery life by not needlessly processing noisy channels, minimizing latency,
and optimizing data flow in ways we haven't seen before. RSLC's selective approach makes this proactive, energy-efficient spectrum management a practical reality, especially for low-power IoT devices.
To truly understand and analytically predict the performance of these new algorithms, the researchers had to tackle a significant mathematical hurdle. The full probability density function, or PDF, which is basically the statistical fingerprint of the received energy under the Nakagami fading model, is incredibly complex. If they tried to use it directly to derive performance metrics, it In simpler terms,
The exact mathematical equations would become computationally unmanageable and practically useless for drawing clear, actionable conclusions about how the system would perform in various scenarios.
So what does this all mean for us, the practical implications? The researchers employed a clever and widely used simplification technique called asymptotic analysis. This allowed them to simplify that complex PDF into a much more manageable, simple expression. Well, for those who appreciate mathematical engineering, this is brilliant. It's like finding a robust, elegant formula that closely approximates a very complicated curve, especially at a critical operating point. It allows for tractable analysis where exact solutions are intractable.
and this approximation is not only acceptable but absolutely critical for real-world application, especially in cognitive radio, where reliability at low signal levels is paramount. The paper rigorously validates this by showing that this approximated PDF almost overlaps with the actual PDF, particularly for low SNR, or signal-to-noise ratio. SNR is basically how strong your signal is compared to the background noise. They specifically focused on scenarios where the average SNR, represented by gamma bar, is less than or equal to
0 dB, meaning the signal is effectively weaker than or equal to the noise. This is incredibly significant because, in order to implement cognitive radio without causing interference to the
critical detection scenarios.
And to combine these multiple ears, or diversity branches, the paper leverages a powerful statistical technique involving their marginal probability density functions, or PDFs. Think of it this way. Each receiver gives you a whisper, a unique probabilistic fingerprint of the signal's presence, along with its inherent noise characteristics. Convolving these PDFs is akin to precisely overlapping those individual probabilistic whispers to generate a single, amplified, and statistically much clearer show. It transforms individual, noisy, and
Potentially unreliable observations from each diversity branch into a consolidated, highly confident decision statistic for that channel, far beyond what any single receiver could achieve on its own.
And it's important to note that this extensive analysis was specifically carried out under the Nakagami feeding channel model. This isn't just a random choice. Nakagami is a highly regarded, generalized fading model in wireless communications. This means it's versatile enough to represent a wide variety of real-world propagation conditions by simply adjusting a parameter called M. It can effectively model anything from the severe signal fluctuations you might experience in dense urban environments with many obstacles to the somewhat less volatile
conditions in suburban areas or even line-of-sight scenarios. This choice makes the paper's findings broadly applicable to many different real-world wireless deployment scenarios.
When we talk about how well a cognitive radio is performing its sensing task, our usual go-to measurements like the probability of misdetection, which is failing to detect an active primary user, and the probability of false alarm detecting a primary user when none actually exists. These traditional metrics aren't quite enough for wideband spectrum sensing. While essential for single-channel sensing, they don't capture the multifaceted objectives and nuances of a wideband system.
Exactly. The ultimate goal of wideband spectrum sensing is fundamentally different from that of simply sensing a single isolated channel. As the paper points out, secondary users in a cognitive radio system may not be interested in finding all the spectrum opportunities across the wideband. For many applications, a fraction of those opportunities might be perfectly sufficient for them to operate effectively. This means that WSS can often tolerate a much higher probability of false alarm than single-channel sensing might. If you falsely detect a primary user
On one of many channels in a wideband, it's not as catastrophic as falsely detecting one on the only channel you're trying to use. It's about finding enough free space to function, not meticulously
So, to address this, the paper, building on crucial prior work, introduces and adopts two new performance metrics that are much more suitable, indeed essential, for evaluating wideband spectrum sensing in a practical context. These are the probability of insufficient spectrum opportunity, or PISO, and the probability of excessive interference opportunity, or PEAO. These metrics go straight to the heart of what truly matters for a functioning, deployable, cognitive radio system, finding enough channels without causing unacceptable interference.
Let's break those down. First, PISO is defined as the probability of insufficient spectrum opportunity, Mathematically, it's expressed as PRS, SST. Here, S represents the number of
Why should you, the listener, care about ISO? This metric directly tells you if the cognitive radio system is finding enough free channels for you to actually use your device or application effectively. Imagine you're trying to make a high-definition video call, and you need a certain amount of bandwidth, which translates to a specific number of free channels. You definitely don't want to be left with insufficient spectrum opportunity, where your call is constantly buffering or dropping. A piezo quantifies the risk that the CR won't find the necessary resources for its intended
operation, directly impacting user experience and application performance.
Then there's PEIO, defined as the probability of excessive interference opportunity. This is PRID. Here I stands for the number of missed on channels. This is crucial because a missed on channel means the cognitive radio mistakenly thought a primary user was inactive when in fact they were active in transmitting. This is precisely when the secondary user interferes with the primary user, a fundamental violation of the cognitive radio paradigm and a major regulatory concern. And I is the maximum number of PU channels on which the interference
from SU is allowed. This IDE essentially sets a predefined, acceptable tolerance level for how much interference the system can permit. It's a critical knob for system designers.
For system designers, this isn't just a technical knob, it's a regulatory tightrope walk. PEIO quantifies how often the CR might step over that line and cause excessive interference, which is something that has to be minimized for any real-world deployment. And this paper gives them a more precise understanding of the consequences of setting that tolerance.
No, to summarize, these two new metrics, PISO and PEIO, offer a much more nuanced and practical view of wideband spectrum sensing performance. They move beyond simple, isolated detection accuracies to focus on the actual real-world needs of the secondary user, making sure they have enough opportunity, while critically also ensuring the robust protection of the primary user by limiting disruptive interference. It's about balancing the usability of the cognitive radio system with its paramount responsibility to licensed spectrum holders. This holistic view is
Vital for future regulatory frameworks.
Now let's get to the truly compelling part. What did the rigorous analysis and experiments in this research paper actually reveal? The overarching conclusion from their analysis is very clear and powerful. The proposed algorithms, both CCSLC and RSLC, which fundamentally utilize diversity, consistently and significantly outperform the traditional channel-by-channel and rank channel detection algorithms that do not use diversity. This conclusively confirms that adding multiple listening points and intelligently combining their information
Truly makes a substantial quantifiable difference in real-world performance under challenging conditions.
Let's look at the numbers because that's where the concrete proof lies. Take the CCSLC performance, compellingly illustrated in Figure 3 of the paper. They meticulously compared the no diversity case, where the number of diversity branches, P equals 1, which is essentially the older channel-by-channel detection, or CCD with CCSLC using more diversity branches, specifically P equals 8. The results are quite compelling and truly underscore the power of diversity. For a specific PEIO, or probability of excessive interference, of
Approximately 0.222, the PISO, or probability of insufficient spectrum opportunity, was about 0.054 for the traditional CCD method. But for
Similarly, when looking at RSLC performance in Figure 4, comparing the no diversity RCD P1 with RSLC using 8 diversity branches, the improvement is also strikingly evident. For a PEIO of approximately 0.040, the PISO was a high 0.544 for RCD, but for RSLC with 8 diversity branches, it was significantly lower at 0.250. This again clearly demonstrates that diversity drastically improves performance across the board, making it much more probable that the secondary user finds sufficient opportunities even under
Challenging fading conditions. The value of having multiple listening points and intelligently combining their inputs, rather than relying on a single vulnerable path, is undeniably validated by these results.
So we've established that diversity is a game changer, but which of the new algorithms is the clear winner? The paper's results also consistently indicate that among the two proposed detection algorithms, ranked square law combining, or RSLC, performs demonstrably better. It's the champion here, offering a superior balance of performance metrics. When comparing CC-SLC with RSLC in Figure 5, for example, at a PEIO of roughly 0.062, CC-SLC showed a PISO of about 0.448. However,
RSLC, that clever ranked method we talked about, achieved a much better PISO of 0.260 for the same interference tolerance. That's nearly twice as good in terms of finding sufficient spectrum opportunities for...
This superior performance of RSLC over CCSLC comes down to its core intelligent design. In CCSLC, the system is mandated to make a decision on all L channels that are being sensed. In contrast, RSLC, after sorting the channels by their combined energy levels, makes decisions on a smaller, strategically chosen subset, LD channels, which are the ones that appear most promising, those with the lowest energy. The paper explicitly states this happens because in CCSLC, we take the decision on all L channels, whereas in
RSLC, we take the decision on only LDL channels. This means that trying to make a decision on a larger number of channels inherently increases the chance of making a detection error, and thus
RSLC is the clear winner for performance. Now let's look at how different environmental and system parameters affect the performance of the superior RSLC algorithm using the detailed analysis in the paper. This is where we get into the real-world implications of understanding how robust this solution is across varying conditions. First, let's examine average SNR, or gamma bar, which we see compellingly in Figure 6a. This result tracks intuitively. With an increase in average SNR, meaning a stronger signal relative to the background noise,
the performance of the sensing algorithm consistently improves, showing a lower PISO for a given PEIO. A clearer, stronger signal simply makes it inherently easier to accurately detect.
Next, consider the occupancy probability, denoted as P, shown in Figure 6b. This P represents how often a primary user channel is actually occupied within the wideband. As P increases, meaning more primary users are active and thus more channels are busy, the number of truly available spectrum holes in the partial band decreases. This logically results in higher interference for secondary users, as it's harder to find truly clear channels and consequently lower spectrum opportunity, leading to a degradation in sensing performance.
if there are fewer holes in the spectrum to find in the first place, it's naturally harder to find them reliably, increasing the chances of both insufficient opportunities and accidental interference.
And there's the number of channels in the partial band, L range, which we see in Figure 6c. This parameter defines how many channels the cognitive radio is looking at within its chosen partial band. The research shows that an increase in L generally results in improved performance, as reflected by a decrease in PISO for a given PEIO. This is because sensing more channels in the partial band simply means there's a greater statistical likelihood of finding genuinely free channels. The more you look across a broad range, the more likely you are to find an open spot.
Crucially, this graph also powerfully validates the pragmatic choice of using partial band Nyquist sampling, or PBNS. The paper observes a significant finding. When L exceeds a certain value, the improvement is not significant, thus validating the use of PBNS. For instance, they note that for L greater than approximately 16 channels, the performance improvement wasn't substantial enough to warrant the increased computational burden. This confirms a key efficiency point for system designers. Since secondary users don't necessarily require all channels for their use,
It's not required or even beneficial from a performance per cost perspective to sense the entire wideband. You get diminishing returns after a certain point, so you can stop sensing more channels and save on computation.
The study also looked at scenarios with varied occupancy probabilities across the channels, which is a very realistic real-world condition for how spectrum is used. Figure 7 and Table 3 illustrate 3 distinct scenarios. All channels have low OP, occupancy probability. Only a few channels have high OP, a mixed scenario. And all channels have high OP, a heavily congested scenario. The results clearly show that the performance is significantly better when all the channels have a lower occupancy probability. For example, for a PEIO of approximately 0.802,
The PISO was around 0.616 for the ideal all-low scenario, but it jumped sharply to about 0.8804 for few highs and a much higher 0.881 for the all.
If we connect this to the bigger picture, this implies a valuable practical strategy for future cognitive radio deployment and network planning. CR systems should be designed to focus their spectrum sensing efforts on groups of channels where the primary user activity is generally known or predicted to be low. By concentrating on these less congested areas, they maximize their chances of finding ample spectrum opportunities while simultaneously minimizing the risk of causing interference. This data helps engineers make informed decisions about
which frequency bands to prioritize for sensing, leading to more efficient and robust CR networks. It's also incredibly important to note that the theoretical analysis
validation for the theoretical analysis carried out. This level of convergence between theory and simulation is crucial for gaining confidence in deploying these solutions in real-world scenarios, as it confirms that their mathematical models accurately predict real-world behavior and the performance of their proposed algorithms.
Finally, let's dive into some practical parameters for the superior R-Res SLC algorithm based on the Monte Carlo simulations shown in Figure 9. These insights are absolutely crucial for anyone trying to design or configure a real-world cognitive radio system, as they reveal the delicate tuning required. First, let's look at LD, which is the number of sevens on which the decision is actually made after the channels have been sorted. Figure 9a clearly shows that increasing LD tends to degrade the performance, meaning the PDOS increases for a given PEIO.
Right. While increasing LA will give the cognitive radio more channels to potentially decide on and use, it also significantly increases the statistical risk of making a detection error, and thus causing interference to the primary users. The paper suggests that it is advantageous to choose LD equals SD, meaning you should ideally only make decisions on as many channels as you desire to find, which is SD. This helps keep the interference to primary users as low as possible and minimizes computational overhead, even if it means potentially leaving some other technically available channels unsensed.
It's about optimal resource allocation versus strict risk mitigation, especially crucial for devices with limited processing power.
Next, we have SD, the desired number of spectrum opportunities. From Figure 9b, it's clear that as SD increases, meaning you demand a higher number of free channels, the overall performance tends to degrade, leading to a higher PISO for a given PEIO. This makes perfect sense intuitively. If you set a higher target for the number of free channels your system must find, the system has to work harder to meet that goal. This often means it has to be less selective, potentially having to consider noisier channels, or taking more risks in its detection process.
This can lead to a higher probability of false alarms or, critically, more interference with primary users, ultimately worsening overall performance in achieving a balance between spectrum access
And finally, let's consider I, which is the maximum number of primary user channels on which interference from a secondary user is allowed. So 9C demonstrates a very interesting and somewhat counterintuitive finding. The performance actually improves as I increases. This is a very interesting and practical trade-off that regulators and system designers must grapple with. If you allow the secondary user to interfere with more primary user channels, that is, if I is greater than 0, meaning a small predefined level of acceptable interference is tolerated,
the secondary user's ability to find spectrum opportunities significantly improves. This highlights the delicate but crucial balance that needs to be struck between the secondary user's urgent need
What's fascinating here is that while diversity offers undeniable and significant performance improvements, especially under fading, it does come at a cost. The paper, in its computational complexity analysis shown in Table 2, details this. It shows that the diversity and
energy consumption in a real device. For a low-power IoT sensor, for example, this increased computational burden could be a significant design constraint impacting battery life, whereas for
However, the key takeaway, as the authors clearly state, is that the performance improvement gained from using diversity justifies the increased complexity. For many, if not most, critical applications, particularly those requiring high reliability, such as emergency services, industrial IoT, or advanced mobile broadband, the enhanced reliability and efficiency in the spectrum usage far outweigh the additional computational overhead. It's not just a worthwhile trade-off, it's an essential investment in a smarter, more robust, and more efficient
wireless future, where reliable connectivity is paramount. The benefits in terms of spectral efficiency and interference mitigation far exceed the marginal increase in processing requirements for many modern chips.
So, to recap the paper's core message, it demonstrates conclusively that the strategic use of diversity significantly improves the detection performance in wideband spectrum sensing, especially under challenging fading conditions. Furthermore, among the two new techniques proposed, the ranked square law combining, or RSLC, consistently outperforms the channel-by-channel square law combining, or CCSLC, by intelligently prioritizing spectrum opportunities.
And the authors, as any good researchers do, outline some really exciting future work, extending this research even further into the complexities of real-world wireless environments. First, they suggest exploring other diversity schemes and more general fading models beyond the Nakagami model they used. This includes more complex scenarios like frequency-selective fading, where different frequency components of a signal experience different fading characteristics across the channel. This is significantly more challenging to model and
mitigate, but is highly prevalent in high-bandwidth communication systems, broadening the applicability of their findings to even more dynamic and complex real-world scenarios.
While a general broadband channel might have a lower priority, an optimization technique would allow the seer to intelligently set its sensing thresholds to reflect these nuanced policy decisions, ensuring robust protection for critical services while still maximizing opportunistic access for other users. It's about fine-tuning the intelligence to align precisely with real-world policy and operational needs. And finally, they envision extending their approach to cooperative WSS, where multiple secondary users imagine an entire network of smart radios, perhaps your phone collaborating with your smart speaker and a nearby
IoT sensor, actually cooperate in detecting the presence of primary users. This would take the concept of smart radios to a whole new level. Instead of each device acting in isolation, they
truly about collective intelligence in the airwaves.
So what does this all mean for you, the listener, and for the future of our connected world? This deep dive shows that intelligent spectrum sensing, leveraging sophisticated techniques like diversity, isn't just theoretical. It's a vital, practical step towards unlocking the full, untapped potential of our wireless world. It promises to make our connected experiences more efficient, more reliable, and dramatically less wasteful, moving us away from a static, inefficient spectrum allocation model to a dynamic, intelligent one. This research moves us
closer to a future where wireless connectivity is not limited by artificial boundaries, but optimized by cutting-edge intelligence.
Imagine a future where every wireless device you own, from your phone to your smart fridge, is fundamentally a cognitive radio. Not only would they seamlessly avoid interfering with licensed users, but they could also actively collaborate with other devices, perhaps a mesh of smart devices across your home, or an entire smart city to use the invisible airwaves with unprecedented fluidity and efficiency. How might this radical transformation in spectrum utilization reshape our daily experience of connectivity, from the densest urban centers where
spectrum is fiercely competed for, to the most remote areas where it's currently scarce or unreliable? What entirely new applications and services might emerge, from hyper-efficient